Okay, back again. We see over here that we've got this 23 newtons per meter. So the newtons per meter there is a really critical thing because that's going to clue you into that is your K value. So I'm going to go ahead and put 23 in after I put the 1/2, obviously. So give me just a second there. So 1/2 times 23. And then the amount that I'm stretched is 0.12 meters, and that's going to be the my x. And so I just plug in the numbers, and then I'll get the answer. So give me a second to get my calculator. And so we're going to do 1/2 times 23 times 0.12 squared. And we get a little number because it's not stretched very far. And so that little number, if I can stop moving everything around, is going to be 0.17, we'll say with sig figs, 0.17. And we haven't talked about the units here. We haven't covered what the units are for energy. Well, the energy we're going to use is called the joule. That's Joule. And 1 joule is going to be equal to 1 kilogram meter squared per second squared. On the next question, I'll show you how we get this. But so there's my answer right there. So not that big of a deal. You just kind of plug the numbers in and you move on. So next energy identification example, I've got a car that's rolling down a hill, and I'm looking at the moment the car is halfway down the hill where it's moving quickly, and I want to know what types of energy there are. So again, if you go back to your questions, we have, is it moving? Is it at a relative height? Is anything stretched or compressed? So if we go through these questions, this one, and I'll draw a little doodle to help us out here. So there's my hill. It's a very steep hill. And there's a box representing my car, and it's going down the hill. Well, first, is it moving? Yeah, definitely, because I've told you that it's moving quickly, right? So I would say yes, there is definitely some kinetic energy there. So definitely kinetic. Second, is it at a relative height? Yeah, like the car could fall that height, right? So there's definitely going to be some gravitational. Anything stretched or compressed? Not that we can reasonably say. So we'll count that one out. So here we've got kinetic and gravitational. And now last to finish this out, we'll do a quick calculation example. And here we're just calculating what we just found. So I've given you, again, some numbers. So I've told you for example, the mass of the car is 1,200 kilograms. The height that it's at it's a 12-meter hill. But be careful here. It says at the moment the car is halfway down the hill. So I actually should clue that into, I want half of that. So maybe I should go ahead and say that my height is 6 meters. And I've given you the velocity at which it's moving. So it's moving at 8 meters per second. And so here, I'm going to calculate the individual pieces, and then I'm going to figure out these total mechanical energy, which I'll come back to in a minute. So the individual pieces are that the kinetic energy is 1/2 mv squared. So we'll just go ahead and plug numbers in there. 1/2. The mass is 1,200 kilograms. And the velocity is 8 meters per second, so times 8 squared. It'll give me a minute for my calculator. So 1/2 times 1,200 times 8 squared. We get 38,400 joules, which is quite a bit larger number, but that should make sense because it is a large car. So it makes sense we get a bigger number. Now the other one, potential gravitational, that's MGH. And if I plug in my numbers here, I've got 1,200 kilograms is my mass times gravity's 9.8. And I'm going to multiply that by the height. And again, the hill is 12 meters tall, but it's halfway down, so it's only 6 meters. And that will give me my gravitational potential energy. So calculator times 1,200 times 9.8 times 6. I get 70,560 joules. Now, the total mechanical energy here, so the total mechanical energy, well, that's just adding up all of the mechanical energy. So if I pull this up a little bit, we normally use a sigma for the total. So the total mechanical energy, it's just the kinetic plus the potential, and it's always going to be kinetic plus potential. If I had spring, I'd include that too, but I don't. And so I'm just adding those together. So it's going to be equal to 38,400 plus 70,560. And again, I'll go to my handy dandy calculator here. So the total mechanical energy is equal to 38,400 plus 70,560. And so we get is 108,960 joules. So that's the total mechanical energy. We're just adding the two up. Now, one last thing before I wrap this up and be done is that I told you we'd come back to this idea of a joule, right? So I told you previously, let's go up a little bit, that a joule is 1 kilogram meter squared per second squared. I think the easiest thing to do here to show you this is a dimensional analysis. So if I come and I use gravitational potential energy for this, mass is measured in kilograms. Gravity is an acceleration, so it's measured in meters per second squared, and height is a distance, so it's measured in meters. Now, if I multiply all those units together, I get kilograms times meters, so kilogram meters squared, and then 1 times second squared times 1, so per second squared. That's how I know that it's a kilogram meter squared per second squared. That's just a bit of a mouthful. We don't want to say that every time, so instead we say, okay, we'll just call that a joule. So there's your overview on energy. So we've kind of covered, if I zoom out so I can find it, this taxonomy of energy classification that I'm just going to briefly review again. So we've got this idea that energy is kind of this currency of motion. It's what you have to be moving or to make something move. And we tend to lump that into two categories. It could be non-mechanical, meaning that it's not usable for motion, or it can be mechanical, meaning that it is motion or it's useful for motion. And then we break that down further into kinetic, so something that is moving, and potential, something that it could easily move. And the two examples we have there are elastic, so something that's deformed, and if I let it go, it will move. Or gravitational, something that's some sort of relative height, and if I let it go, it will move. So the idea is all I have to do is get out of its way. That's why it's potential. And then we looked at some examples of calculations, right? So here's our equations once again, and we've done some examples of how to identify the energy that's present. Remember, these three questions are critical, and then we've actually gone ahead and calculated them. So that's all for this video. Sorry about the audio issue, and I'm sorry about the multiple clips issue. In case you're curious, the palm rejection on my computer wasn't working well, so I was accidentally leaving the window, and it was just stopping the recording. So, lesson learned. Next time I'll be more careful. So let me know if you have questions. We'll discuss in class tomorrow.